In this example, we will find the volume of a solid that is not a solid of revolution. We will find the volume of the solid whose base is an elliptical region with boundary curve 9x squared plus 4y squared equals 36, and cross sections perpendicular to the x-axis are isosceles right triangles with hypotenuse in the base. This is a problem directly out of your textbook. It's number 55 from section 6.2. The first thing you need to do is draw the base. So we know that this curve, 9x squared plus 4y squared equals 36, gives us the outline of the base. If you want to recognize this in standard form, this is x squared over 4 plus y squared over 9 equals 1. I just divided everything by 36. You could use Desmos to graph this if you'd like. This ellipse will intersect the x-axis at 2 and -2, and it will intersect the y-axis at 3 and -3. Okay, so this is the base of our solid. Now, it tells us something about the cross sections. The cross sections are perpendicular to the x-axis, so our cross sections will attach to the base this way. Each cross section we'll think of as having a width delta x. And so what you're imagining is if this ellipse is flat on your screen or flat on your table, then on each vertical slice there is a triangle sticking up out of either your screen or your table that makes this into a solid. We are told that each of these cross sections is an isosceles right triangle with the hypotenuse in the base. A right triangle, we know, means that one angle is a 90-degree angle. Isosceles means that two sides of our triangle have the same length, and the hypotenuse is the third side. So this is the base of our cross section that you're imagining being glued onto this strip here. Okay, let's do this. What we want to do is we want to find the area of this triangle as a function of x. So I want this to be a function of x. I want it to be a function of x because we're slicing our solid with vertical slices of width delta x. So I know that in the end I'm going to have some kind of integral with a dx. So I need everything in terms of x. Okay, well, let's see. We know that the area of a triangle is 1/2 base times height. Let's see. We know the base is the blue line here, or in other words, blue over here. And I can tell that if I look just from the x-axis up to the top, that this has height y. And then because of the symmetry of the ellipse, this also has height y. So the base is 2y. So we have 1/2, the base is 2y. Okay, and then the height is this. And if you look at this right triangle, this is also an isosceles right triangle just from symmetry. This leg has length y, and so this leg also has length y, which is all just to argue that the height of our triangle is also y. So overall, the area of our triangle is y squared. Okay, except remember that we want it in terms of x. Okay, so this y value is the y value of this point x comma y, and we know that this point is on the ellipse, the curve of the ellipse. Therefore, we want to take this equation and solve for y squared in terms of x. I'm going to go back to the original equation for our ellipse. We have 9x squared plus 4y squared equals 36. I'm trying to solve for y squared, so I'm going to subtract 9x squared. And then divide by 4. Okay, if I wanted to solve for y, I could then take the square root of both sides, but because I really want y squared here for my area, I don't need to. So the area a of x is 9 minus 9/4 x squared. Now we are ready to find the volume of our solid. Remember, in general, the volume is the integral from x value a to x value b of the area of a cross section at x times dx. So we have, for our problem, the integral of, we figured out a of x is 9 minus 9/4 x squared dx. And for the bounds a and b, that's the far left end and the far right end. So a is -2 and b is 2. So we integrate from -2 to 2 the quantity 9 minus 9/4 x squared. Okay, using the fundamental theorem of calculus, our antiderivative is 9x minus 3/4 x to the third. We evaluate at -2 and 2. Plugging in 2, we get 9 times 2 minus 3/4 times 8. And then we subtract 9 times -2 minus 3/4 times -8. Simplifying all of this gives us a value of 24 for the volume of this solid.